Yeah, hello. Now let us look at visualization of quantitative data in R. Okay. Yeah, so as usual, I have the code available here for you. So if you look at the lecture 6, you are able to copy all the codes and then you can practice along. Okay. Yeah, so first of all, what we are going to do is to be able to get our data, which we are going to use this line of the code to be able to get our data. And the data is CSV file. So we are using the CSV read.csv, and then we have the choose file, which is going to open a window for us to select our data, and then with the header of the data equal true, and we are assigning it to hints data. Okay, so let's run that line of code. So this is the hints data. I selected now, it's available for use. You can look at the names of the data. We have 17 columns, and then you can look at the summary of the data. By looking at the summary of the data, you can see there are some unwanted information, which is -9, which is also said to be missing information or data. So we might want to get rid of it. Now, so to proceed with cleaning the data by choosing variables we would want to analyze and also getting rid of unwanted information from that variable, let's first of all attach the data so that we wouldn't have to always use the $sign to pull a particular variable from the data. So from there, we are going to create a new data in which we are naming it hints data underscore new, okay? And then now we'll go into the original hints data in which we have imported, okay? And then within it, okay, we are going to use the concatenate function, which is C in a bracket. We are able to clean all the variables we are needed for our analysis, so quality of care, insurance, and we want to exclude the negative. So we say quality of care, which is a categorical variable greater than 0, which will allow us to exclude the negatives. Health insurance, age, gender, full-time occupation, BMI, smoking status, exercise, and then drinking. And then we use this end sign to be able to actually separate them. And then thereafter, we bring the comma sign to let R know that, okay, we still need all the columns within the data set, even though we are cleaning this variable of the data. Okay, so let's go ahead and run it. So once we have run it again, we can run, we still have the 17th columns of the data set, but we can run the statistical summary to see, and then we can see that now over here we have the negatives, okay, for quality of care, insurance, age, but once you go down here, we don't have the negative anymore for those variables we chose. So which means now the data is good for us to proceed with some kind of analysis, okay? So let us attach this new data so that we'll be able to use every variable within the data without making use of a $sign to pull that variable, okay? So now R is able to store that variable within its memory, and that if you mention that variable, it understands that variable, okay? So now let us start with plotting some quantitative variables, okay? Visualization of some quantitative variable. So first of all, let us look at stem and leaf plot, okay? Stem and leaf plot is able to allow us access the distribution of the data, okay? Just like histogram and then boxplot. So with stem and leaf plot, we are able to, now even before then, now we can look at the dimension of the data, okay? So the dimension of hints new, okay, underscore new. So data dimension of the data, we have 2,738 observation and then 17 columns, okay? I did this because I wanted us to look at, once we use the stem function, we want to find the stem and leaf for age, okay? So we can run. So this is the stem and leaf one for age. And you can see if you have a very large data set, stem and leaf plot doesn't actually ideally help you better understand the distribution of the data. So that wouldn't be advisable. If you have a small data set, you can still use stem and leaf plot to be able to visualize and understand the distribution of that data. Now let us look at histogram. So you use the hits function. So hits of age, okay? So let us look at hits of age and then let's run it. So this become the histogram of age. Let me enlarge this a little bit for us to see, okay? So this is the histogram, which is fairly normally distributed, okay? And then we can also color it, okay? Rather than having this gray color, we can decide to choose our own color. And then at the same time, you'll be able to actually give it some name, okay? So the name within the hit function, it's of which variable age. Then the main is the title we are giving to the to that particular histogram, which is going to be histogram of age or maybe distribution of age. I would also use appropriate name that become very meaningful when communicating to others. And then the color, we are using the pink color. I mean, you can make a choice of any color, maybe blue, red. You just put it in the quotation marks, okay? Okay, all right, so let's run it. So here is what we have, the histogram, and then we are having the frequencies on the y-axis and then the ages on the x-axis, okay? So the y-axis tells us the frequencies of the different age groups, okay, of the different ages. Okay, so now we can also proceed to actually get some probability. So rather than getting the frequencies of the age, we might want to have some probabilities, okay? So with that, we are using a different variable, which is the BMI variable, okay? And then we are going to label the x-axis, which is really the x lab, which we put in a quotation, which is the BMI level, and then the main, which is the title of the histogram, which is histogram of BMI, which again, you can say distribution of histogram. Then color, we are choosing some color for, okay? And then we want the border. So you can actually use numbers to also depict colors, and every number you choose, either 1, 2, 3, 4, 5, it gives you different type of colors. And we want the border of the histogram to be green. And then we want the probability. So we would want to see the probabilities rather than the frequencies, okay? So we say probability within the frequency function equal true. So now let us run this line of the code. Okay, so now you can see that we have the border of the histogram is green. We have also the probabilities rather than the frequencies, and then there's also the BMI level, okay, which start from 10 and then upward. Okay, you can also include grade, okay, just to also make it quite pretty. So there's also grade, okay, by adding some grade to make your plots prettier. Okay, we can also have a density plot. So rather than having this histogram, we might want to see some kind of a curve, okay, showing the density of the that particular variable, the density distribution of that variable. So in order to do that, we want to look at the density for age. To do that, just even before, you can see that in terms of interpretation of this plot, you can see that, I mean, it's fairly skewed to the what? To the right, okay? And then maybe probably there could be some potential outliers within this particular BMI or histogram. So that's something to deal with when in case you have to perform further analysis. Anyway, now let us look at getting the density plot. So to obtain a density plot, we have to create our density values, okay? So we use what is called the density function, and then we are assigning it to density estimate, okay? So that density function allows us to get the density value or the estimates of the densities for age, and then now we run it. So now this time, we are no more going to use age, we are going to use the density estimate we created for age within the plot, okay? So we say plot density estimate for age, And then we are actually going to give it a title, which we said the title is our density of age. And then we are taking some color equal 4 with the X label, which is the values, and then the Y labels representing the what? The densities. Okay, so let's run. Okay, so there is the density for what? For age, okay, with the density values on the y-axis, or the density estimate, and then on the x-axis is the values of the age, okay? Now, so this is for histogram. Now let us look at what about Boxplot, which is also another graph used in displaying a quantitative data or a continuous variable, okay? So let us look at, if we are interested in looking at the Boxplot of age, okay? And then we want the box plots to be horizontal, okay? And then we are going to give it a title, which is called box plot distribution of what? Age, okay? Now we are going to use the function called the box plot function to be able to get the box plot, okay? So let's run it. So now this gives us the box plot. Now the box plot, remember, allow us to be able to even observe the 5 member sum, right? To be able to know the minimum, the first quarter, the median, the third quarter, and then the maximum value. And then it also allows us to even assess the skewness of the data. And you can see the median is a little bit shift to the right. So it tells you that there's some little skewness to the left, right of the data. Anyway, now, next, assuming we want to see a side-by-side distribution of the data, okay, we are going to use a function which is called the par function. Within it, we are going to create a vector which we have mflow, an argument called the mf call, okay, the mf call, which means we want one row and then 2 columns, okay? And this allows us to be able to, let's say, create a side-by-side plot of, let's say, histogram and then box plot of age, okay? So let's run this line of the code. Now we can go ahead and run the histogram of age, and there's the color we want, the forest green color. And then also this, we are giving it the title histogram of age, okay? And then now we also run the box plot using the box plot function, box plot of age. We want the color to be pink, deep pink, okay? And then also deep pink. And then also we have the title to be B, which is what the panel B, which is box plot of age. So let's run it. So now we have age here, and let's run, we have box plot here. So you can see now they are sitting side by side, and it is actually showing the same, it's allowing us to assess the distribution of age, okay, but using both the histogram and then the box plot sitting side by side. Okay, so now what about if you want to actually display a quantitative variable side by side box plot, okay? Let's say you would want to actually display a quantitative variable for a qualitative, for a categorical variable, okay? Let's say we have age, and we want to display the distribution of age for both male and female within our gender group, okay? So in this case, now let us bring our panel back to one panel rather than 2 panels. So we have to go back and then use the par function with this argument mf call. Now instead of over here 1, 2, we are doing it 1, 1, and that remove from a 1 row 2 columns to 1 row round column, which is 1 big or a single panel. Okay, so now here we would want to display a box plot of age, but we want the age to be by gender, okay? We are displaying the box plot of age, but by gender. So let us look at it. And then we use this sign, which is the approximate sign, and then birth gender, which is the variable within our data set. Okay, so let's run. So you can see we have gender 1 and gender 2. 1, I believe, is male, 2 is the female, and we are able to assess what is the distribution of age for the male, what is the distribution of age for the female. And then you can see that, at least from here, you can see that the median age, the median for gender one, which is male, the median age is a little higher than the median age for the female. And then that's how you are able to even make some analysis based on observing this visualization. Now, next, we can actually also look at, let's say, a box plot for age and quality of care, okay? Now, the quality of care is a categorical variable. So we would want to have a box plot of age for quality of care. And then we have the data, okay? Now, within the box plot function, we can introduce the data, which especially if you are dealing with several different data sets, but you want how to ensure that R is using the right data set, you can introduce the data equal, and then you give the data name, okay? So the data we are using is the hence data underscore new, okay? That's the data we are using. And then we want to give the X lab to be quality of care, and the Y lab to be what? To be age, okay? And then we are using the name to be distribution of age by quality of care. And then we want some rainbow colors, okay, to be given for the different categories of the quality of care. And then these are the names for the quality of care, which is excellent, very good, good, fair, and then poor, okay? All right. So now let us run. Okay, so here's what we have. So now we are able to observe this, the distribution for the various category of quality of care, the distribution of age for the various category of quality of care. You're able to assess the median age for each of the category of quality of care, and even their distribution, whether it is right skew, left skew. Yeah, and I mean, if you look at the distribution of fair quality of care for the age, it is almost normal, just like also the good quality of care. And then very good is fairly normal, but you can see that poor is quite left skewed, because you can see the median is actually very close to the third quartile, right? And then the excellent is also a little bit fairly skewed, but not that skewed, okay? But it's skewed also to the left. Now, okay, so let us also look at plotting some kind of different charts, okay? In terms of box plot, how you can actually visualize different type of box plot in different ways. So let us use the power function. Again, we want to create 1x2 panel, okay, which is 1 row and 2 column panel, okay? So let us use this power function. We run it. And then now we want to create a box plot for BMI for the individual quality of care, okay? And then we pull up our data set. Our X lab is the quality of care. Our Y lab is the BMI. So we are looking at the distribution of this has to be the distribution of BMI by quality of care. And then we have the notch, which is going to give you some beautification of the plot, and then also the var width. And then we have the color. So these are the different colors we are actually choosing. Now we are no more using the rainbow 5, but we decided to create a vector of our own colors, which is red, yellow, green, blue, and then pink. And then this is the names of each of the colors. So we create a vector of names for the category of quality of care, okay? So let us run it. Okay, so this is what we have. And in this case, now we are able to even observe the some outliers. We're able to assess whether this box plot has some outliers. And you can see beyond the maximum, all these circles you see after the maximum value, it's a potential outliers within the data, okay? Now, this actually gives us a vertical box plot, okay? What if we want our box plot to be horizontal? So rather than being vertical, what if you want it to be horizontal? Now, if you want it to be horizontal, it's just simple. You just have to introduce another argument, which you said horizontal equal true. Okay. Now we are changing our color. We are no more giving our own colors, but we are asking how to make a color choice from 1 to 5. Okay. But again, we are using the concatenate function, which is a vector of the color choices. Okay. And again, this has to be the distribution of BMI, okay, by quality of K. But then we want to see it in a horizontal form. Let's run it so you can see. Now, this is showing the distribution of BMI, okay? And then now we are seeing it in horizontal rather than what? Vertical, okay? All right, so now, next, let us actually look at giving names to the data, okay? So we would want to actually look at giving names to each category of the quality of care rather than having it to be 1, 2, 3, 4, okay? So for instance, if we decide to find a factor, the factor of let's say summary of the factor of quality care. Now let's run it and see. So you can see we have it 1, 2, 3, 4, 5, right? I mean, 1, 2, 3, 4, 5 is not meaningful. But now we would want to create another column in which we have a meaningful names for each of the category of the quality of care, right? So we go to our clean data, which is the hints underscore new. We use the $sign to create a new variable, which we have it as quality of care underscore new, okay? And then now we use the square bracket, we go into the data again, and then we put up the quality of care within our clean data, which is equals to 1. And now we are going to assign it what? Excellent. So all what we are saying is we are creating a new variable called quality of care new from the original variable quality of care, which is equals to 1, should be assigned excellent. The same way, the quality of care, which is equals to 2, should be assigned very good. The quality of care, which is equals to 3, should be assigned good. And then all the way to 5, which should be assigned poor. And they should all be placed in a new variable called what? Quality of care new, okay? So now let's run this entire code, okay? You can run it one after the other. So now we can actually decide to, we can first of all decide to even look at the names. Oh, oops. So we can decide to look at the names of the hints data, okay? So let us look at the names of the hints new data. You can see now we have a new variable which have been added, which is quality of care new, right? Now, initially we have 17 variable columns, but now we have 18 columns, okay, which was the new variable we actually created. So we can actually decide to find the summary of the factor. Now remember, whenever we introduce factor, we want R to understand that it is a categorical variable, right? Yeah. So we want to find the summary of the factor of the quality of care new, okay, from our hints new data, okay? So now here we have it, okay? So there is it. So now we have, instead of 1, 2, 3, 4 initially, we now have excellent, fair, good, poor, and then very good, okay? Which have been actually given to us in categories. So now we can now go ahead and then plot a more meaningful, have a more meaningful plot, okay? To understand the quality, the distribution for age based on quality of care, the individual categories of quality of care. But I mean, before we do that, we can first of all, before we do that plot, we can change our panel from a 1x2 panel to what 1x1 panel, which is a single panel. Okay, let's run it. Now let us run the box plot by for age by each of the quality of care. Okay, again, we are going into the hints new data. Now we are giving it the X lab to be the quality of care, the Y lab to be the age in years, and then we have the distribution of age by quality of care. So let's go ahead and run it. So here's what we have. So you can see. Okay. So now let us actually look at, we can also, in a different example, let us try to create our own kind of a data set where we have the length, okay, of the data. So we are creating a length, which is a vector of length, okay? So we have created length, we are assigning a vector of length to length, okay? And then we have using the concatenate function that allows us to create that vector, okay? So let's run it. And then we have type. So type, it's a variable, which is of course a categorical variable, but we have type from 11122, okay? So there's a variable we are also creating and assigning it to type, which is a vector containing type 1 and type 2. So now, again, we can decide to plot a box plot of the length by the type, okay? And then we are giving it the name of sycamore and sugar maple leaf, okay? And then we are assigning the Y lab, the label of the Y to be length in centimeters, and then we want the color to be green, okay? So you can go ahead and plot. So this how you can also easily create your own kind of data and then plot, okay? So now moving away from box plot, now let us look at how about creating a line plot, okay? Now to create a line plot, we are going to use a data called the biomass data, okay, which is also in CSV file. So we are going to use this read.csv, then choose.file to open up a window in our computer and then select our data. So let's run this line of the code. Okay, we can minimize this. Now there's the biomass data. So we can double click on the biomass data and then go back to our R. Okay. So now what we can do is, again, we can attach the data so that we wouldn't have to use $sign to call the variable each time. So let's attach our data. Now we can observe the names of the data, and then we can observe the head of the data, which gives us the first six observation of the data. Now we can just make a plot of STBM, which is a continual variable, a quantitative variable, okay? So they just give us a plot of kind of a scatter plot along with its index, okay? So by just creating a plot of a single continual variable, R automatically create a kind of a scatter plot along with their index, okay? So now let us look at creating, so along with this, we can actually add some kind of colors, okay? And then the type of how we actually want to observe the points in the plot, okay? So within the plot function, we want to plot the STBM, the type we are using the O to give a different points style. And then we have the color, we are choosing red. And then now you are having the label of the y-axis to be the estimate, and then the title, which is the main, to be line plot of data, okay? And then we are choosing PCH to be what? To be 1, which is also a different style in terms of how the points are plotted within are plotted. Okay, so let's go ahead and plot this line. Okay, so now we are able to plot the line plot, okay? So now by using the type, by using the color, now we are able to generate lines Initially, we couldn't generate lines through it, right? But now we are able to generate lines through it to be able to observe how does it actually looks like, right? And then make some analysis, right? So at least over here, you can actually observe there was some form of decreasing, and then, I mean, some kind of steadiness, it increased, and then, so there's a more fluctuation kind of a plot, okay? So you may not make a lot of sense from this, but again, now you have a line plot. Now, we can also create several line plot within the same panel, okay? So what we are going to do is, again, we can go ahead, create this same line plot, which we have here, but we want another plot to be embedded on this plot, okay, rather than creating a new plot. So we are going to use a function called the lines function. So lines of what? This variable, which is RTBM, okay? And then we said that type, again, we are using type equal O with give us blue line, and then the PCH equal 2, which give us a different, I mean, style or look in terms of the points, okay? Let's plot so you can see. So if you want to maximize this, you can actually maximize this, and then you can use the zoom to maximize it and actually observe it. Now we can close, okay? So now you can also, for it to be even more meaningful, what does the blue color represent and what does the red color represent? So we can use the legend, okay? Where the legend, we would want to actually plot the legend in the bottom right corner, and then the legend of what? Of the two variables in which we plotted, okay, the lines plot, the legend of those two variables. And remember, for each of those variables, it have been plotted based on their index, okay, the estimate and then their index. Okay, so we want within the legend function, we have legend equal the two variables, a vector of the two variables, and then we have the 6 equal 1.3, which how bigger we want the legend to look like. And then we have the different colors. So now we said we have this right here represent color red, and this right here represent color blue. Okay. And then now we have the PCH, which over here, the PCH of 1. Remember, we have the PCH of 1 here and the PCH of what? 2. Okay. So now within the legend 2, we would want to also introduce the what? The PCH, which is a vector of 1 and 2. Okay. Then we close the legend. So now let's run this line of the code. Okay, so now you can see. So they become more meaningful, okay? So you can actually decide to even change the name of the name of the plot, which is a line plot of what STBM and RTBM by their index. Okay. All right. Now let us look more into scatter plots correlation. Okay. So now away from line plots, which I mean, if you think about line plot, you can even think more about analyzing trend plots, okay, in the future, where you have let's say you have years, and then you have some values, and then you want to assess the trend, which is something you can actually assess them to using, I mean, line plot. Okay, so now let us look at some kind of correlation, scatter plots correlation, okay? And we know correlation, which is just like scatter plot. Scatter plot allow us to assess the relationship between, I mean, two variables, right? Two continuous variables. So, for instance, in the scatter plot, this one is allowing us to assess the relationship between the estimate of the variable and then their index, right? Now, in the same way, these are all kind of a scatter plot, but again, we are able to introduce the line in it. But now let us look at plotting a scatter plot of these two variables, which is assessing the relationship between the TBM and then RTBM rather than assessing the relation based on their index, which would make any much meaning. Okay. So we are assessing their relationship, and then also this PCH again, it actually changes the style how you would want to observe. For instance, we have this circle here, we have this triangle here. PCH equal 19 give us a different style, okay? And then now the color equal factor. Now, within the biodata, this variable here, which is the C, is a factor. So we would want to plot a scatter plot of these two variables, looking at the relation between these two variables. But again, we also want to be able to observe within that relationship the C variable, okay, for that relationship. So let us look at it. So now you can see. So we are able to observe the relationship between these two variables, which you can see that maybe it's they have some kind of positive relationship. But again, we are able to observe the C factor here is telling us the different categories, which of those categories represent 1, 2, and then 3 within the C category, okay? Now we can actually put a legend, which we want the legend to be at the top left corner. So again, we said legend, and then we said the legend equal the levels, okay? The levels, which we want the legend to represent the levels, unlike here where the legend was STB, and then RTBM. Over here, we want the legend to represent what does the blue color, the red color, the black color represent. Now we are assigning within the legend, we are assigning an argument which we said this legend should be representing the levels of C, which the C categories. Again, using the PCH, which is equal 19, which gives us this style. And then the color, again, is we are giving a color by the levels of the factor, okay? So now let us run. Okay, so now we are able to observe. So black color represent 1, red color represent 2, green color represent 3, and then the blue color represent 4 categories within this, okay? So we are able to observe the relationship between RTBM and then STBM, which is kind of a quite positive relationship. And then we are able to observe it by the cluster of the C categories, okay, the C variable. Now let us look at a more kind of advanced way to observe a scatter plot, okay? Now we can also look at, so to do that, we are going to use a package called a car package, which you have to first of all install if you don't have it already, and then you load that package. So I have it, so I just have to load that package. Now, rather than using the plot function to create our scatter plot between the two variables, we can use a function from the car package, which is called the scatter plot function, okay, to create this scatter plot. So let's run it. So now we are able to get a more advanced scatter plot. Within it, we have a smooth, we have a line which we are able to observe the relationship very well, which is a regression line, okay? And then we are able to get confidence interval, okay, around, the line which have been actually drawn. And then we are able to observe the Boxplot distribution for RTBM, which is on the Y panel, and then the Y-axis, and then the Boxplot distribution of STBM, which is on the X-axis, okay? And now we are able to observe the relationship between RTBM and then STBM. So there's a more advanced way to also observe. Now, further, we can actually be even more creative by saying that, okay, we don't need the smooth, okay? So we are going to actually remove the smooth from the from the graph, from the scatter plot, and then also we don't need the regression line, okay? We don't need the regression line to observe the differences. So within the scatter plot function, yes, we want the scatter plot of these two variables. Again, we would want to maintain the PCH, which is equal to 19, which is a style color. We want the color to be 1, but we want to remove the smooth line, and then we want to remove the regression line, okay? And so now let us go ahead, and then you can write all this code in one line, but I just use the enter to actually create it in separate lines for a better understanding. Okay, so let's run it. So you can see. So now there is no regression line, there's no smoothing, there's no the confidence interval that was actually created. But again, we're able to observe the relationship. We're able to see the distribution of RTBM, the Boxplot distribution of STBM. Okay, so next, let us also look at from the hints data, which is a more real-world data set. We'll be able to observe, which is a population-based data set. We are able to observe the relationship between age and BMI. So the question now becomes, what is the relationship between age and BMI? And always you have to be careful whenever you are actually assigning. Now, the first variable is the X variable, and the second variable is what? The Y variable, okay? And so you would want to know whether age can predict BMI, right? But not BMI can predict age. So if you choose to bring BMI at the X as the X variable and age as the Y variable, and that means you'll be displaying a wrong plot, okay? So that's something you have to take note of. Before you plot a scatter plot, you have to be able to understand which variable is the dependent variable and which variable is the independent variable. The independent variable is the X variable, which always predict the Y variable, which is the dependent variable, okay? So we want to know the relationship between age and BMI. So we say age versus BMI, which is not very meaningful. So you can decide to make it more meaningful by saying that relationship. So you can say relationship between age and BMI, right? That become also more meaningful. Again, always give your plot a meaningful. I can choose to use I can enter to bring a less line of the code so that it wouldn't have to be too long. Okay, so the X lab is the age, the Y lab is the BMI, and the color trace you are using is what? Green. And then again, you are maintaining the PCH equal 19, but we can change the 19 to 1, and then you can see we are going to see not a deep circle points, but we are going to see something different. Let us run it and see. So let's run this line of the code. So you can see this line of the code. So now, what if we actually want to, so there's a distribution of age and BMI, which actually it is not really, we are not able to really observe any kind of relationship, right? Any kind of major relationship. So maybe you might want to say there is no relationship between age and BMI. But regardless, we can also have 2 or more scatter plots on the same panel, okay? So what if we would want to observe, we have the relationship between age and BMI, but again, on the same panel, we would want to also observe the relationship between drinking and then BMI, the relationship between exercise and then BMI, okay? So the y-axis variable remain the same, but we would want to actually ensure that we have different points on the same plot that is showing different x variable, right? And so with that, we are looking at these different variables, which is drinking and exercise, as they are all independent variable, okay? And then we are all looking at whether they have some relationship with BMI, okay? So first of all, we can run this line of the code. Okay, so let's run this line of the code, which is looking at age and BMI. Let's run it. Then next, let us run the next line of the code, which is looking at drinking and BMI. But now we are using what is called the point function that embed this relationship on the same panel, okay? But we want to observe it using the blue color with the PCH equal 2, which will give us a different style of points, okay? So now we can see. And then next, we also want to be able to observe the relationship between exercise and then BMI, okay? Weekly moderate exercise and BMI. Again, we want to observe it on the same panel, but with the color of green and then a PCH of what? 3, okay? Let's run. So this is how you can actually, and then you can actually see that the drinking and then BMI versus BMI, it is actually showing some kind of clusters, right? Which make you think maybe some kind of maybe categories is actually happening here in terms of the relationship between BMI and then weekly moderate exercise. Okay. So now even to make it more meaningful, we would want to include legend, okay? So to include the legend, remember, we want the legend to be at the top right corner of the panel. And then remember, we were finding the relationship was on age, alcohol, and then weekly physical exercise, okay? And so, and then the points, the colors were blue, red, and black. So we create a vector of the colors as well. And then let me bring the PCH here. And then the PCH was 1, 2, 3. So we also create the vector of the PCH also as well. Okay. So we create a vector of the legend within the legend function. This is how large we want the panel of the legend to look like. The vector of the colors for the 3 variables, independent variables, and then the colors, the PCH, which is the style of the point that has to be plotted, okay? Let's run. So now you can see we have it at the top right corner. So we are able to understand what blue represents within this plot, what the triangular red represent, and then what the plus sign actually represent. Then we can even include some grade, okay? So we can actually include some. So you have the grade function 1010 that gives you some grade style, which you can actually see. But you can choose different numbers. You can just try and error and then see that you are going to be able to observe different grade style, okay? Okay, all right. So now let us look at if you are creating our own data, okay? Let's create our own data, which we are creating it altitude, okay? So altitude, which is a vector we are creating by using the concatenate function with comma separating them. And then we have the RBC, which is also another variable we are actually going to create, okay? Now we can be able to plot to see the relationship between altitude and RBC, okay? Yeah, which is the red blood cell, okay? So we want to observe the difference, the relationship between these two. And then by so doing, so let's look at it by using just the plot function, okay? So plot altitude, and this. So this is how, so this is the relationship. So we can say that the relationship is, they have some kind of positive relationship, right? But then we can also be able to observe the correlation between altitude and then the red blood cell, okay? So in this case, we're looking at whether the altitude predicts the red blood cell, which is RBC, okay? So to observe the correlation, we use what is called a call function, call of altitude and then RBC, okay? And that gives us the Pearson correlation coefficient. So the correlation is what, 0.8, which is kind of, it is having pretty high positive correlation or relationship between, these two variables, okay? But then we can also proceed and then plot the relationship between these two variables in a very stylish way, and we can, so let me enter here too. So now we are plotting altitude, giving it the name scatter plot of X versus Y, which we say altitude versus RBC, which is the red blood cell. Let's say we're giving X lab to be X variable, Y lab to be the Y variable, and then you have the PCH to be 19. We have a color of pink. Again, in a project, make sure X, if you give X label as X variable, Y label as Y variable, it's meaningless, right? You have to give it the right name. So we could have just chosen to give the name of altitude versus RBC, which is the RBC will be the Y axis, and then the altitude will be the X axis. But there's also a scatter plot in which you can actually observe. Okay. Okay. All right. So I will see you in the next lecture with more visualization on correlations. Okay. See you.